Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition, and I'm up to problem 2.11. In this video we're going to do problem 2.11 and problem 2.12. So let's get on with it. Problem 2.11, it's asking to show that the eccentricity is 1 for a rectilinear orbit. So a rectilinear orbit is one where the spacecraft or object is moving directly towards the mass. So there's no angular momentum in that case. So h bar equals 0. And to demonstrate that the eccentricity is 1, we're going to use an equation from the book. It is on page 71. And it is r plus, the magnitude of the radius plus the radius vector dot the eccentricity vector equals h squared over mu, the gravitational constant. And to demonstrate that the eccentricity is 1, we're going to set h equal to 0, so that equals 0. And so now we can see that, this here must equal minus r, so r bar dot e bar equals minus r. And then there's another equation, which is your standard equation for getting an angle between two vectors. We have r dot e equals r e cos theta. So we know that is minus r equals r e cos theta. So we can cancel the r, we get minus 1 equals e cos theta. And we know that since we know that this is a basically negative 1, we know that the vectors are opposite each other, right? So theta equals 180 degrees, and then so that's minus 1 equals the cos of 180 is minus 1, so that's minus e, so e equals 1. And that's it. And that is 2.11. If you have any questions, let me know in the comments, or if you think I've made a mistake, let me know. Next question is 2.12, and that question is asking us to find, for a non-rotating Earth-centered Cartesian coordinate system, the velocity of a spacecraft with velocity equals minus 4, 3, and minus 5 kilometers per second. And it has a direction of radius, so a unit vector radius of 0.26726, 0.53452, and 0.80178. And that's unit vector direction. So let's just draw this out. So here is the focal point of the orbit. Now we don't know what kind of orbit it is, but it shouldn't matter. So then we have the radius here, the direction of it anyway, and then we have our body here with, let's say, just a velocity just like that, right? So this is actually really straightforward, right? What we're looking to get is, what it's asking us to get is the radial component of velocity. and the azimuth component of velocity. Now the radial component is this one here. So we'll call that, sorry, that's the azimuth component is here. That is the perpendicular one. That is, sorry, V with an upside down T. And this one here is the radial velocity. Now the radial velocity is in the same direction as the radius direction. So it's quite simple. We're just going to project this velocity onto this vector here. And to do that, we go back to chapter 1 where we see the equation for projecting from one vector onto another is a b equals a dot b over like this. So what we will do is say the velocity equals, so the velocity mapped onto the radius equals the velocity vector dot product with our unit vector r. That becomes a bar dot ub, unit vector b. So, and when we work that one out, we get Vr equals minus 3.474 kilometers per second. And that is the answer in the book. In order to get the azimuth component, we just take the velocity minus the velocity r, and the radial velocity equals this times unit vector r. So unit vector r times our magnitude of radial velocity equals our vector radial velocity. And when you subtract the velocity vector minus the radial velocity vector, you get, and you take the magnitude of that, you get 6.1586 kilometers per second, which is again what's in the book, so that's right. And then it asks you to get the flight path angle, and if you look in the book for that, there is a whole section on calculating that, but it's basic trigonometry, and the equation for the flight path angle is inverse of tan and the radial velocity magnitude divided by the azimuth velocity magnitude. When you do that, you get minus 29.43 degrees. Yep, that's it. If you have any questions, leave them in the comments, or if you think I've made a mistake, let me know. Thank you very much. Goodbye.